So welcome to the video on how to represent molecules or how to draw molecules on a two-dimensional surface. There are many different ways that we can do this. The first and kind of most basic is the Lewis dot structure. This is something we talked about in last chapter. So the Lewis dot structure is the very basic, complete representation of organic molecule on paper. So once we start getting more advanced in the way that we draw the structure, we can actually partially condense it. So for example, this CH3 right here becomes CH3. And so you can see that it's CH3 connected to a C, connected to a CH3. But please note that on the left-hand side, that CH3 is actually written H3C because the carbon is bonded to the carbon. And then this carbon is also connected to our OH and our H. So that's what's called a partially condensed structure. The fully condensed structure is sometimes a little difficult to understand at first, but here is our central carbon, and off of it is two methyl groups, one H and one OH. And so you could see how that fits together. And then finally, our molecular formula. This might be something we think of from Gen Chem, where we have how many carbons, how many hydrogens, how many oxygens, but they're not really put in any order. And so if you think about drawing that molecular formula out in structure, you really don't have any information. And so that molecular formula could actually be a couple of different structures. And if you see below, all three of these compounds have the same molecular formula, but they have a completely different structure. In this situation, we have this OH group off the central carbon. That's called a hydroxyl group or an alcohol. In the second molecule, we have the OH group, the alcohol, off of the end carbon. And finally, over here, we don't have an alcohol at all. We have an oxygen that's sandwiched in between two carbons, and that's called an ether. So it turns out that the way that these three molecules are related is called constitutional isomers. So we have constitutional isomers right here. Same molecular formula, different molecular structure. And so if we take one step further, so it's beyond condensed and partially condensed, it's actually going to be the way we're going to start drawing all of our organic molecules, and that is called the bond line structure, and that is shown here. So this structure above is the Lewis dot structure of this molecule, and shown below is the bond line structure. I also refer to this as the line bond and or skeletal structure. You can see, I hope, that this is so much easier to draw, first of all, and to see. In both cases, the skeletal structure or the line bond structure is easier to deal with. Now, the question is, how do we get from one to the other? And so that's what I'll show you now. How to read line bond structures. So first of all, each corner and or end is a carbon. So as we walk along this line bond structure, we can see that there are 6 carbons. In this molecule over here, we see that there are 4 carbons. And over here, we also have 4 carbons. And for a double bond, the corner looks similar to that of the single bonds. And for the triple bond here, because we know that that's linear, we're going to have to look at this intersection as a carbon as well. The zigzag format shown here and here is very typical for representing sp3 and sp2 hybridized atoms in a carbon molecule, and then the linear geometry shown here in our alkyne. Carbon atoms are not labeled, so we never write a carbon in, and we assume that all of the hydrogens are attached to that carbon as needed. If we walk through this molecule, this carbon right here, carbon number 1 on our alkane, must have 3 hydrogens because carbon needs 4, and there's a single bond right here. So we have 3 additional spots, and so we assume any end of a line bond structure, that carbon has 3 hydrogens. If we see a corner right here that is bonded to 2 different carbons, then there are going to be 2 hydrogens on that carbon. Remember, carbon always has to add up to 4, and anything that's not drawn on the line bond structure is assumed to be a hydrogen. If you look over at the second molecule, the alkene, this carbon right here, carbon number 2, has 1 bond to the carbon here and 2 bonds over here. So we only have 1 left. And so this carbon number 2 is just going to have 1 hydrogen on it. And if we walk over to our carbon number 2 in the alkyne over here on the right, we see that this carbon right here has 1, 2, 3, 4 bonds already. So there is no room for any additional hydrogens. And so in that case, we don't have any hydrogens on that carbon. So H atoms are not shown, but it is always assumed that there are enough to complete the octet, which, as I just mentioned, is going to be 4 bonds to each carbon. So if we walk across the molecule shown right here, this carbon right here is going to have 3 H's to fill the octet. This carbon right here is going to have 2 H's to fill the octet. This one also is going to have 2 H's to fill the octet. And this end one here is going to have 3 H's to fill the octet. If we were going to draw the hydrogens in, which we will not, but if we were, just to show you, they're drawn in red below. So I want you to try practicing here. And again, you can pause your video, but see if you can identify the location of the carbons and the hydrogens in these skeletal structures. In your mind's eye, you should see the hydrogens and where they're located. So at some point, these are going to start becoming very natural to you. At some point, you're just going to look at these structures and know how many hydrogens, how many carbons. It's just going to become natural, second nature. But again, just like riding your bike, you can't just watch me do it. You actually have to practice and see. So pause your video now and determine the location of every carbon and how many hydrogens are on each carbon. I will label all of my carbons with a green dot. So there's a carbon here, 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 and here. We have 6 carbons in this molecule, and the 2 end carbons are going to each have 3 H's. Central carbons here with the circle are each going to have 2 H's. And so now we have all of those carbons with filled octets, and we're all good. So if we identify our carbons, 1, 2, 3, 4, 5, 6, we see that all of the end carbons have 3 H's. The 2 carbons here with the circles have 2 hydrogens. And now watch this. This carbon right here with the triangle only has 1 hydrogen. It already has 3 bonds. 1, 2, 3 bonds. So what's left? 1. And so the triangle indicates 1 hydrogen. If we go over to the third molecule over here, if we draw in our carbons, we have 1, 2, 3, 4, 5, 6. The 4 carbons that are at the end all have 3 H's. And the 2 in the middle, because they already have 3 bonds, only have 1 H. Now, if we take a very advanced molecule down here at the bottom, I hope you can start to see, I will indicate in green all of the places where there's a carbon. So these are all carbons. And if we walk through the molecule now and start thinking about how many hydrogens, we have 2 here, we have 0 here, we have 0 here, we have 1 here, we have 0 here, we have 3 here, we have 3 here, we have 0 here, we have 2 here, we have 3 here and here, and we have 0 here, we have 0 here, we have 1 here, and we have 0 here. One thing I didn't mention is anytime you have a heteroatom that is not carbon, oxygen, nitrogen, sulfur, or any of those types atoms in your molecule, you do in fact write the hydrogen attached to those. So anytime you have a heteroatom, we include the hydrogen that is on the heteroatom. And of course, down here we have chlorine. Chlorine needs to be included as well. So the only atoms we do not write are the carbon and the hydrogen. Carbons never get written. Hydrogens only get written if they're on a heteroatom. And then every other atom from the periodic table does need to be included in these line bond structures. How to draw line bond structures? The first rule is the sp2 and sp3 hybridized atoms have to be drawn in a zigzag format. So if we have C4H10, it's just 1, 2, 3, 4, and we assume all the H's. When drawing double bonds, draw the bonds as far apart as possible. And so this is not how we would do it. Typically, we have a double bond, and we think about bond angles of 120. And so we're going to want to put those substituents or those other groups in that kind of 120 format. So this is not good. When drawing single bonds or sp3 hybridized carbons, The direction in which you draw the bonds is irrelevant. So these two things are actually identical. In both cases, we have a central carbon with CH3 above. Now we have a CH2 with a CH3 and a CH2 with a CH3. We have a CH2 with a CH3, a CH2 with a CH3. Those are actually identical as long as it's in the zigzag form, and it doesn't matter which way, which is different because up here with the alkene, we want to make sure we draw it as far apart as possible. Rule number 4 is all heteroatoms other than carbon and hydrogen must be drawn in, as well as any H attached to them. So here's the Lewis dot structure, here's the line bond structure. And because that hydrogen is on that oxygen, we actually include that in the line bond structure. Rule number 5, never draw more than 4 bonds to any carbon atom. Remember, octet rule. It's kind of funny because you'll see that when I'm grading exams, if I write the word yikes on your paper, that means that you have a carbon in that answer that has more than 4 bonds. So you'll never see a situation where carbon looks like that. This does not happen. So remember, we have to follow the octet rule and never have carbon atoms having more than 4 bonds. Again, we assume the hydrogens, but you'll never have more than 4. There you have it, line bond structures in organic chemistry. Good luck.